In this part of the lecture, we're going to continue with our discussion of virtual memory. Some of this is going to be rather monotonous, so don't get too worried about if you don't catch every bit of it, because some of it is kind of just overview, kind of like a survey. So, how can we improve demand paging optimization? How can we make optimizations on it? Well, we can use, well, if we use specialized swap space I/O instead of normal system I/O, it can be faster. Basically, it allows you to allocate larger chunks and not have to deal with anything like directories or pathing or anything like that. One other thing is you could copy the entire process image to swap space at process load time, so that way you can page in and out of swap space. Older Unix used to use this. You can also bring in a demand page from program binary on disk, but discard rather than paging out when freeing the frame. What it means by that is basically because we know the program isn't going to change, we can just get rid of it and reload it as we need it. But you still do need to write swap space for pages not associated with a file, memory, or pages that have been modified but not yet written back. Once again, with mobile systems, they don't typically support swapping. Instead, they demand page from the file system and reclaim read-only pages. So, one approach to all this is copy on write, and it allows both child and parent processes to share the same pages in memory. If either process modifies a page, then only the page is copied. If you think about that for a second, the advantage to that is we only keep differences. It allows more efficient process creation as only modified pages are copied. Free pages are allocated from a pool of pre-allocated on-demand pages filled with zeros. If the pool has free frames, we can do fast page execution. Why do we want to zero out a page before allocating it? Because if we don't, what could end up with is we could have garbage in there, and it might be possible to walk off the end of the process and do some bad stuff. vfork is a variation on fork in Linux, and has the parent, suspend, and child using copy on write. And it's designed to have the child call exec on the process, and it can be very efficient. So here, we've got our process 1 and process 2, and they're sharing pages before somebody modifies page C. And afterwards, we'll have C and a page of C where the process points to the changed one. What if we have no new frames? If we've used them up, how do we deal with this? We page replacement, find some page in memory but not in use, page it out. Options are to terminate it, swap it, or replace the page. We want an algorithm that will result in a minimum number of page faults. We want to make sure that we minimize how many pages of same pages are brought in memory at the same time. We can prevent over-allocation of memory by modifying the page fault service routine to include page replacement. Now we have a dirty bit instead of just an invalid bit, and it only is only used when we write pages to disk. We only modify or write dirty ones. And page replacement completes the separation between logical and physical memory, and large virtual memory can be provided on a much smaller system. So here we load page M, or we try to, it's not there. And so therefore we're going to end up having to go here and load it from there. Memory 2 still uses the same frames. And if it tries to load us something that has an invalid bit, it will force us to go fetch from the storage. So here's the basic algorithm. It's find the location of the page on disk, find a free frame. If there's free one, use it. If not, we have to use an algorithm to find our victim. We write the victim frame to disk if it's dirty. We bring the desired pages into the new free frame, update the page frame tables, and we continue the process by restarting the instruction. So basically, here we go. We've got 1, swapped out victim page. 2, mark it as invalid. 3, swap in the desired page. And 4, reset the page table for the new page. There's a couple different algorithms you can use. It determines how many frame allocation algorithms determines how many frames to give to each process and which frames to replace. Page replacement algorithms want the lowest page fault rate on both first access and re-access. We evaluate algorithms by running it on a particular string of memory references and computing the number of page faults. The string is just page numbers, not full addresses, because that's not what we're testing. Repeated access to the same page shouldn't cause a fault, and the results depend on the number of frames available. In these examples, we're going to use the reference string shown below. Here is the graph of the number of page faults versus the number of frames. And the lower the number of frames, the higher the number of page faults, which makes sense if you think about it. So in a first in, first out algorithm, which is one approach, we could have 3 pages in memory at the same time. So then first 7 would come in, 0, 1. Then we'd swap out the first one because it's first in, first out. Then the next time we'd swap out the second one, and so forth. Obviously, how this works can vary by the reference string, and can cause things to go in and out of memory, causing a thrashing effect. Adding more frames can cause more page faults. That's called Belode's anomaly. How to track the age of the pages? Well, first in, first out by default gives you the age of a page. Here's Bell's anomaly. As we get the number of frames increasing, after a certain point, it starts to actually impact the number of faults, like here, for example. So, what if we had an optimal algorithm? It will be to replace page that will not be used for the longest period of time. For the example above, 9 is optimal for the above example. How do you know this? Because we can't read the future, and we can only use this for measuring how your algorithm performs against the ideal situation. The reality is you cannot have an optimal algorithm without pre-knowledge, which we don't have. So another option is the least recently used algorithm. This allows us to use past knowledge rather than the future. We replace a page that has not been used in the most amount of time. And we associate the time of last use with each page. So we'd have to have this more information. So here we got 7, 0, 1. Then we have 2, which will replace 7. 0, nothing needs to be replaced. 3 would replace 1 because it's the least recently used. 0 wouldn't replace anything because it's still in memory. 4 would replace 2, which is our least recently used. Then 2 would replace 3, which is our recently used, and so forth. This will cause 12 faults. It's better than FIFO, but worse than the optimal of 9. But generally it's a good algorithm. So here's the general algorithm. Every page entry has a counter. Every time a page is referenced through this entry, copy the clock into the counter. When a page needs to be changed, look at the counters, find the smallest value, but this requires us to search through the table. Another option is a stack implementation. Keep a stack of page numbers in a double link form. When a page is referenced, move it to the top. It does require up to 6 pointers to be changed. That is the 2 for the front, 2 for the base of the stack, and potentially 4 for the actual moving of the item. It does require an update to be more expensive, but no search for replacement. However, least recently used and opt are cases of stack elements that don't have Belode's anomaly. We don't pay a price for adding more frames. So here we use our stack 47012 470 which we replace the most recent page references. Basically these are showing the most recent pages referenced. 4 would follow to stay at the bottom because it's not referenced again, and then similarly 0 as we go through would be moved down to near the bottom again. So another option is to use least recently used approximation algorithms. LRU really needs special hardware and is a bit slow. So what we can do is with each page associate a bit, initially 0. When it's referenced, set it to 1. Replace any with reference 0 first, but we don't know the order. The other thing is to use a second chance algorithm. Generally, it's FIFO plus a hardware provided reference bit. We'll use the clock to drive our replacement. If a page has to be replaced, if its reference bit is 0, we replace it. If it's 1, then we set the bit to 0 and leave the page in memory, and we replace the next page subject to the same rules. So here we would find our next victim and then replace it, and if it was 1, we'd continue on until we found an actual value we could replace. And then the original would be set to 0. We can improve this algorithm by using a reference bit and a modified bit as an ordered pair. Okay, so if it's not referenced and not modified, it's the best page to replace. Not referenced but modified, we need to write out before replacement. Referenced but not modified, it's recently used but clean, most likely would be used again. And 1.1 is recently used and modified, so we would need to write it out before replacement. When page replacement is called for, use the clock scheme, but use the 4 classes, replace each page in the lowest non-empty class. Basically, we might have to search through a couple times, but find the result that causes the least amount of reads and writes. So for page buffering algorithms, we should always keep a pool of free frames. Then, when we have frames that are available, we don't have to go into a false state. And then we can read the page into a frame and select the victim to evict and add to a free pool. When convenient, evict the victim. Much faster that way. We could even keep a list of modified pages. When the backing store is otherwise idle, write pages there and set to non-dirty. Possibly keep free frames, contents intact, and note what's in them. And if it's referenced again before it's reused, no need to load the contents again from disk. This can generally be used to reduce the penalty if the wrong frames are accepted. So one thing about it is all these algorithms have the OS guessing about the future. Some applications have better knowledge. For example, databases. Databases generally know where the next data they need to read is because of the way queries are formed. They can actually predictively pull stuff. Memory-intensive applications can sometimes cause double buffering. The OS keeps a copy of a page in memory, and the application keeps a copy for its own work. An OS can be given direct access to the disk and get out of the way of the applications. Raw disk mode is an example of this. Oracle database uses it. This bypasses buffers, locking, etc., and leaves the application responsible for that. Allocation of frames. Each process needs some minimum number of frames. Example, back in the day, the IBM 370 needed 6 pages to handle SS move instructions. The maximum frames is the total number of frames in the system. There are 2 major allocation schemes, fixed allocation and priority allocation, and many variations, and we'll start going through some of these now. Fixed allocations are equal allocations. For example, if there are 100 frames and 5 processes, each one gets 20 frames. We keep some in a frame buffer pool. Another option is proportional allocation, allocated according to the size of the process. This can be dynamic as the degree of multiprocessing process size change. So if Si is the size of the process Pi, S is the total sum, M is the total number of frames, then the allocation for P of I is defined as the size of the process divided by the sum of the size of the process times the number of frames. So here's a simple example using that. If we have 64 frames and a 10 frame process and another 12 frame process, a 127 frame process, A1 would be 4, and here A2 would be 57, so the minimum number of frames we'd need. So we could also have a priority allocation, use a proportional allocation scheme using priorities rather than size. If process Pi generates a fault, we select a replacement for one of its frames, and we select a replacement from a frame from a process with lower priority. This could result in lower priority processes running much slower if we're not careful. Okay, another option is global versus local allocation. Global replacement, the process selects a replacement frame from the set of all frames. One process can take one from another. But process execution times can then vary greatly, but you'll improve throughput. Another idea is each process selects from only its own set of frames. And you get a more consistent process performance, but you could end up with some underutilized memory in other processes. So far, we've only talked about equal memory access. Some systems are NUMA, the speed of access to memory variables, non-uniform memory access. Consider system boards containing a CPU and memory indicated over a system bus. Operable performance comes from allocating memory close to the CPU on which the thread is scheduled, modifying the scheduler to schedule the thread on the same system board whenever possible. Solaris handled this by something called iGroups, which we're not going to go into much detail in. So this finishes part 2, and next we will go on to part 3.